right? That is the level 3 analysis. So we already have gone through all 3 levels of analysis. Level 1 is about the printer where we feed the papers in and then we get the papers out, right? It's very simple, only one step and only one flow unit type. In the second level, we look at a car wash process where there's only one type of cars going through, right? All cars are treated equal, so we only have one flow unit type, and then but they have to go through different stages, right? So it's a little bit more complicated. But at level 3 is very complicated because we have both multiple steps and multiple flow unit types. But I hope that with the table, right, we know what to do. It is a sequence of steps that we have to go through. And then because the sequence is clear, so it's not that hard for you to go through when you do this at home, when you do the homework.
Professor, okay. You're not sharing your screen.
Oh, yeah, I have not. Sorry. So we're already done with the 3. Thank you for reminding me. So we are done with the 3 level of analysis, and today we are gonna go to the final part of the module 4. Okay, it is about efficiency measurements, and we're gonna talk about this example. And let me share that with you. By the way. Is that C, right? I just wanted to give you the credit point. All right, so today we move on to the final part of the module 4 about efficiency measurements. We would do some calculation, and at the end, the very, very final part of the module 4 is about process improvement, okay? So those are the things that we need to go through today. So let's work on this example, and this will be very similar to question 25 in your homework, right? We have one more time, we have the hand car wash process. In this case, I just say here enough demand, meaning that we have plenty demand. We don't have to worry about it. What constrain our business here is our capacity, right? So we have a hand car wash process. We know the processing time. We have the number of workers, and there's something new here. It is a hourly wage, right? And we have to calculate the cost of direct labor. That's a new concept. Labor content, idle time, and total idle time, right? And finally, we have to calculate this very important measurement of efficiency. It is an average labor utilization. So we would work on this together. All right, so we have right, we already covered question 23, 24, and today we go to question 25, right? Okay. So we are still in module 4, the final parts of it about process analysis. And the big topic that we talk about now is efficiency measurement. And in this case, we just focus on the labor efficiency, okay? So our example is on slide 45. It is another hand car process. So what we are doing next is we are following the table structure in question 25, right? It is a sequence of steps that we have to do. And then please think about the table as my assist to everybody, because the table gives you the clear sequence of calculation that we have to do. Right. So it is a table like this. And we have the resource number 1 and 2, 3, and the entire process here. Right. So the station number 1 will be our soaping station, 2 will be the rinse station, the 3 will be the dry station. Right. And of course, we use the first column for the long variable names. The very first line is the processing time in terms of how many minutes per car per worker, right? So how many minutes it will take a worker to process one car through that station, or that station. So we have the following. We have 5 minutes here. We have 6 minutes here. We have 4 minutes here, right? And then the total of these has a good meaning, but because we do not need it now, I would cross it out. Later on, we're going to talk about that as a new concept, but for now, we do not need it, right? So that's the processing time. It takes 5 minutes at station number 1, 6 minutes at 2, and 4 minutes at 3. The second line tells us the number of workers. Right. We have 1 worker at station 1, 2 workers at 2, and 1 worker at 3. So this is our decision right here, right? How many people in total that we hire, and how we assign the work to them, or how we allocate the workers among the 3 stations, right? So as a manager, we would make this decision. Okay, and so after we have the number of workers, then we can add them up, and in this case, we hire a total of 4 workers, right? The third row tells us the hourly wage. This is a little bit new, right? Because we have not talked about this before. So we talk about how many dollars we pay per hour per worker. So in this case, right, I base our example from the book, but I modify the values a little bit to make it clearer for us to learn the concepts. So these numbers are different from what you see in the book. So we have $15 per hour per worker at the first station. We have $12 an hour at the second station. And we have $13 per hour at the third station, right? So in this case, possibly the soaping step or station has worked the hardest. So we would like to give the workers over there $15 per hour, and then dry $13 an hour, and then the rinse station only $12 an hour, right? It's just based on the nature of the work. Okay, so we have, or sometimes it's the intensity of the work, right? Some people have to work very fast because of the nature of the work. Then we should pay them more. So that's an hourly wage, and of course the total of these 3 numbers doesn't have any meaning. So we would cross it out. Okay, so that's the basic information about the question, the fundamental information. So the next step is, whenever we deal with a multiple step process like this, or in other words, we talk about the level 2 analysis here, right? Then we always have to find the bottleneck. And to find the bottleneck, we need to know the bottleneck because we need to determine the capacity of the process, right? So to find the bottleneck and to find the capacity of the process, you know what? We have to calculate the individual capacity of the resources first, right? So let me write out here. The next step is the capacity in terms of how many cars an hour. So it's very similar to question 23. I hope that you are totally clear with that question. Please feel free to share your answer about station number 1. In 1 hour, how many cars that station 1 can handle through, right? How many cars that station 1 can soak up in 1 hour? Please feel free to share your answer in the chat window. So what will be the answer here? It's very simple, similar to what you do in question 23. Okay, so I have that from Ferdinand, from Sophia. Do other students agree with these answers? C and Christopher also have the same thing. Good. Karina, the same answer. Solin, Jose. Good. So we all agree. That's a very good thing, right? And, okay. So how to formally calculate it? Let me write the question with you, right? So we talk about how many cars an hour. And in 1 hour, we have 60 minutes. So I would write out that hour 60 minutes, right? And then we know that we can handle a car every 5 minutes. So we take 60 minutes divided by 5 minutes per car. But remember, this is only for one worker, right? So we have to multiply it up with the number of workers. Fortunately, in this case, it is also only one worker. So we have that times 1, and then we have 12 cars an hour. So that's the capacity of station number 1, right? And by the same token, we're going to do the same for station 2, station 3. So here are the answers. So we have 60 divided by 6, and then time 2, right? Because we have 2 workers at station 2. So we have 10 times 2, then we should have 20 cars an hour. At station 3, we have 60 minutes divided by 4 minutes per car. And then because there's only one worker, so the final answer here is 15 cars an hour, right? So by now, we already know the individual capacities of the 3 stations, right? Then we can determine which one is a bottleneck, and then based on that, we can determine the process capacity. So the bottleneck is the resource with the smallest capacity. So in this case, the bottleneck is the resource number 1, which is a soap station, right? And then if we talk about the process capacity, then the process capacity equals the capacity of the bottleneck. So we have that 12 right here. Of course, that's a very important number. So we circle it, we do it with a different color, right? So our capacity is 12 cars an hour, even though station 2 and 3 can handle more than 12 an hour, but the substation can only handle 12. So for the whole process, in 1 hour, we can only handle 12 cars through. Okay, so that's the capacity. We need to know that before we can do anything else. Okay, So after we have the capacities, now we can calculate the flow rate, right? To calculate the flow rate, we need to know the input rate, the demand rate, and of course the process capacity. But then in the question, I only say like enough demand. So I would like to do it a little bit specific. In this case, we assume that the demand rate is 25 cars an hour, right? So let's continue with our table. Again, we have the soap station, the rinse, the dry, and we make up another column for the whole process, right? Okay, so we assume that the demand rate to be 25 cars an hour. Right, so we say here the demand is 25, 25, and 25. Now we should determine the flow rate, right? In terms of how many cars an hour. Okay, so I would like to remind everybody about how to find the flow rate. The flow rate is the minimum among the input rates, process capacity, and the demand rate. In this case, right, we assume the demand to be 25 cars an hour. But you know what? They are both the demand and the input because they are available to enter the process. So they are the input too, right? So the input rate is 25 cars an hour. The process capacity, we got earlier to be 12 cars an hour. And the demand rate is 25 cars an hour, right? Then the flow rate is 12 cars an hour. So that's how we have that 12 right here. And then those 12 cars will move on to station 2, and those 12 cars will move on to station 3, right? The same number everywhere. The flow rate are the same, right? And if we look at the whole process, we see 12 cars coming out of the process every hour, right? Or we see every hour, we see 12 cars coming in, and at the same time, we also see 12 cars coming out. So that's the flow rate, right? The next step, we would calculate a very important number. It is a cycle time. How to calculate the cycle time? I would like to remind everybody that the cycle time is calculated as 1 divided by the flow rate, right? Whatever flow rate that we find earlier, we just take 1 divided by that, then we have the cycle time. So let me dedicate one slide for the cycle time because beside the calculation, we also need to interpret the cycle time in the way that we're going to use in the next calculation. So in terms of the cycle time, then we take, so the cycle time equals 1 divided by the flow rate. And the flow rate, we take it from the previous answer, right? We have 1 divided by 12 cars per hour. That's a flow rate. The hour will be flipped up, so we spend 1 hour for 12 cars, for every 12 cars, right? So that's the cycle time. But then if we take 1 divided by 12, it's going to be a decimal number. it's really hard to grasp the decimal number. So we would convert the hours to the minute, right? So that's why later on we calculate the cycle time as how many minutes per car. So 1 hour is 60 minutes. We take that divided by 12 cars. So eventually we have 5 minutes per car. Right, so that's the cycle time. What does that mean? So another opportunity for us to review the concept, right? Let me draw our process as the following. So the car is coming in, the car is coming out. Here, the boxes represent the cars inside the process. Not all cars are under operations right now, right? The first three should be under operation, but the fourth one is already in the line waiting for their turn, right? Okay, so after every 5 minutes, then the first car, after the 5 minutes, right, the first car will exit, the second car will go here, the third car will move here, the fourth car will be here, and then the next car will come in, right? So that's the cycle time. And then another 5 minutes, the second car now is here, will exit, and then the next car will go there, the next car will go here, the next car will go here, another car will come in, right? So so that's the rhythm of the process. Every interval of 5 minutes, then the whole line will kind of move up by one position. So let me make the note here. After every 5 minutes, the whole line will move up by one position. By one position, right? After 5 minutes, your car will go to the next station. And then another 5 minutes, the car will go to the next station. And that means the following. And this is what we need for our next calculation. It means that the cars will show up in front of you for 5 minutes to work on, right? Or the workers have 5 minutes to work on each car. So just imagine that we are the workers at this facility. Then the car will show up in front of us for 5 minutes. We work on it, right? During those 5 minutes, no more than 5 minutes, because if we work for more than 5 minutes, we're gonna delay the pace of production, right? So the car will show up in front of us for 5 minutes. They will stay there for us to work on. And after 5 minutes, the car will move to the next station, and then the next car will show up in front of you, and then you start working on the next car, right? So that's the concept that we understand the cycle time. How much time the unit stay at each of the station, right, for the workers to work on. All right, so let's go back to the previous part of the table. So now we know that the cycle time is 5 minutes per car. Is an important number. So let me use another color here. All right, 5 minutes per car. And the next time is we can calculate the following. We're done with the basic part of the basic calculation. Okay, after we get the cycle time. And now we can talk about the cost, the labor cost, and the labor efficiency of the process, right? So the first thing that we can do next is the paid time in terms of how many minutes per car. So guess what? We pay the workers to work from 8 a.m. to 4 p.m., right? Or if they have a break in between, then from 8 a.m. to 5 p.m. So cars will go and will go in and exit, right? Will go in and exit. So every 5 minutes you see another car that shows up. Another 5 minutes, another car shows up. So in a sense, right, we really pay the workers to work for 5 minutes per car because you pay them to work for the whole workday, and then every 5 minutes a car will show up in front of them, right? So the paid time in terms of how many minutes of work per car is going to be 5 minutes, right, for one worker. So the paid time at station 1 is 5 times 1. 5 minutes per worker, and we have only one worker, right? Then the paid time at station number 1 is 5 minutes per car, right? At station 2, so by the way, the 5 here is coming from that 5, okay? That's a cycle time. We interpret that's 5 as how long it stay in front of you to work on, right? So in this case, we have 5 times 1 worker equals 5 minutes paid time. And at station 2, we have 2 workers, so we scale this up by 2, and we have 10 minutes paid time at station 2. At station 3, we have only 1 worker, so we have 5 times 1, right? Then we have 5 minutes paid time at station 3. So so let's recap. We pay the single worker at station 1 to work for 5 minutes per car. At station 2, we pay the 2 workers to work for a total of 10 minutes per car, right? And at station 3, we pay that worker to work for 5 minutes per car. So so the total has some good meaning, right? We would add 5 plus 10 plus another 5, then the total paid time. So total paid time will be 15, right? Minutes per car. Right, so I'm sorry, 20, not 15, 20. We just add things up. 20 minutes per car. We hire workers to work from 8 a.m. to 5 p.m. So if we look at each car, then a car will have the for each car we pay the workers to work for a total of 20 minutes. So that's the pay time. The next step is we can calculate the labor cost. So the labor cost is measured as how many dollars per hour that we pay for the workers to work for us, right? This calculation is easy. We know that we pay the worker at station 1 for 15 minutes per hour, and because there is only 1 worker, so we multiply that. So the labor cost at station number 1 is $15 an hour. At station 2, we pay each worker for $12 an hour, and because there are 2 of them, so we incur a cost of $24 per hour at station 2 in terms of the labor cost. And at the station 3, we pay $13 an hour, and because there is only one worker, right? So this number should be $13 an hour. So these are the individual costs at the stations. And then at the end, we would like to add them together, right? So we take 15 plus 24 plus 13, then the total cost will be $52 an hour, right? So we hire the workers, of course, it costs us money. And that cost is $52 per worker on the labor. Okay, so after we find the labor cost, now we can calculate a new concept here. We call that as the cost of direct labor. Or CODL. And we measure this in terms of how many dollars per car, right? When we, in any business, it's gonna cost money to produce the units. Or in this case, it's gonna cost money to process the cars through or wash the cars through. And here we talk about the labor cost, right? So we would like to know how many dollars that we spend on each car in terms of the labor cost. Because we're not interested in the individual resource, we would cross them out. And we really look at the whole process and how costly it is to hire workers on each car, right? So we cross this out. So let's think about it. We want to see how many dollars we spend on each car. Then we already know that in 1 hour, we spend $52 on the labor, right? Then we take that $52. So $52 per hour. And in that same hour, we know that there are 12 cars going through. So we write here as 12 cars per hour, right? The 12 is coming from here. That's a flow rate right there. So again, let's recap. We know how much it costs to hire the workers in 1 hour. And in the same hour, we know how many cars going through, right? So when we divide that by that, we're gonna know how much money or how many dollars that we spend on each car. And the result in this case is $4.33 per car, or $4.33 per car, right? So we call these number as a cost of direct labor. In terms of the labor cost, how much it is to process one flow unit through. Right? So that's the meaning of that $4.33. Let's think about this number a little bit. Why is that important that we have to calculate it? What to do with that number, right? So I would like to ask the whole class, what to do with that number, or why is that important? It is an open-ended question, so please feel free to have any thought in the chat window. So what do you think about that $4.33 per car? Why is that important, or what to do with it, right? Why do we have to calculate it? Please feel free to share your thoughts in the chat window. So think about it. We are the manager of this process. What does that $4.33 per car mean? From time to time, I guess some of you would need to go to a car wash process, right? And you're gonna have some charge for the service. So what does this one do? What does that number do? That's correct, fee. That's the labor cost on average per car. But beyond the labor cost, do we have other the cost too, right? So please think about it. What does that number do? That's correct, Philip. That's part of the cost. Because beside this, we will have other costs, right? Then, of course, at least we have to charge $4.33 per car, at least, so that we can recuperate the labor cost, right? But of course, beside the labor cost, we also have other costs. For example, okay, so to show it will benefit the community in the end. Okay, Karina, that's good too. For example, to calculate the profit margin, right? Okay, brilliant. Yeah, that would be clearer. And Sophia, to know the price of the products and services. That's good. Yes, that's good. Yeah, it is an open-ended question, so any answer will be good here. So think about it. If you are the manager of this business, right? We take that $4.33 as a basis, and then we add on the cost of operation. For example, the cost of the equipment. If you are doing accounting, the cost of the equipment shows up as a depreciation of the equipment, right? So, so cost of equipment, and then cost of materials like chemicals, like cloth and other kind of materials to wash the cars, right? And then on top of that, we have the utility costs like electricity, gas, water, right? So all of those will add up all of the cost of operations per car. Then definitely, whatever the charge is, the charge has to be enough to cover the cost. But on top of the cost, we invest money in this business. We need to have some profit, right? So on top of the cost, you're gonna add some profit margin for yourself, like 25% profit margin, right? So assume that at the end, if we total everything up, then you have $10 per watch. So that $10 cover the cost and cover the profit margin that you want to have, right? But please keep one thing in mind. The charge per watch does not only depend on what we have internally in our process. We also have to look around at our competitors, right? Because if we charge too much per car, then the customer will go to other facilities and they will not go to us. So we will need to look at our own cost, our own desire for the profit margin, but then we also look at what other car wash facilities charge the customers, right? So that you will come up with a so-called optimal charge for you. Not too much, because that will be hard to compete with the competitors. But should not be too little, because too little will cut into your own profit, right? So the $4.33 here is a good number to start with, and then on top of that, we can calculate other items and eventually. By the way, also look at the competitors and eventually come up with a good price, right? Good charge per watch or good price for a unit that we sell. Right, so that's we call that as a cost of direct labor. In terms of the labor cost, how much it is per unit. Oops, sorry, trying to make this column kind of straight. All right, so we're done with the cost of direct labor. It's a new concept, but I hope that it is not hard to calculate it. Right? If we are conscious about the unit of calculation here, then at the end we know that it is $4.33 of labor cost per car. All right, so let's continue with the next part of the table. Now we are ready to calculate the labor efficiency. Okay, so let's move on to the next part of the table. Okay, so we also have station 1 right here, and then 2, and then 3, and the entire process here, right? And one more time, we need to have a very big column at the beginning for the variable names. So next, we talk about the labor content. It sounds a little bit kind of remote, a little bit kind of fancy, right? What is that labor content? So the labor content tells us the required work time per car. In terms of the symbol, we would call this as a LCT. It's just an acronym, right? And what it tells us is the required work time per car. So let me use another column. And we measure this in terms of how many minutes per unit or per car in this case, right? And actually, this is the processing time that the question gives us. We don't have to calculate it. We just copy the information that we have earlier, and then we are done with this row. So earlier they say that the processing time at station number 1 is 5 minutes. So it means that the car requires 5 minutes of stopping time, right? No matter how many workers we have over there, but in total, the minutes of work among the workers will be 5 minutes, right? Because one worker can work on the left-hand side, another worker work on the right-hand side to cut down the time by half. But then if you add the time of the two workers together, it's going to be a total of 5 minutes. So that's the labor content at the first station. At the second station, the labor content is 6 minutes, right? To rinse the car. So remember, there are two workers. So each one of them would have to work for 3 minutes per car. But then, because there are two workers, right? So the total minutes of work at station number 2 would be 6. So that's the labor content at the rinse station. And the labor content at the dry station will be 4 minutes per car, right? It takes 4 minutes of work to go around and dry off the car. So we call that as a labor content. And the total has a good meaning. It is a total labor content, right? Or we just call that as a labor content. So the labor content is the total. So if we add it up, 5 plus 6 plus 4, then we have the labor content 15 minutes for each car that we process through, right? Or as I said here, it is how much time it is necessary to process one car through. And in this case, we calculate that as minutes of work, not just the clock minutes, okay? This is a minutes of work per car. All right, so the idle time, the next line here is we can calculate the idle time. The idle time tells us how many minutes per car that the workers do not have to work. That's why we call it as an idle time, right? So it is measured in how many minutes per car. So later on, we can calculate the individual idle time, or IDT. And then we can also calculate the total idle time, or TIDT, right? So how to calculate the idle time at station number one? Let's work on the number one together, and then I would like to ask you that for two. So let's look at the station number one. Okay, that's a soap station, right? We pay the workers to work on the car for 5 minutes. So that's why we have the pay time of 5 minutes right out here. We pay the workers to work for 5 minutes per car. And actually that's a cycle time, right? How long the car stays in front of us for us to work on it? It is 5 minutes per car. That's the pay time. And then we pay the workers to work for 5 minutes. And then how many minutes that the workers have to work on the car, right? And the labor content tells us that the worker actually work for 5 minutes per car. So if we take the pay time of 5 minutes per car minus the actual work time of 5 minutes per car, then we can find the idle time, right? In this case, the idle time is 0 because it means that the workers have to work the full 5 minutes. And because the nature of the soaping activity, it takes 5 minutes to soap up a car. So the workers do not have any idle time at all. He or she have to work all the time, right? So that's the idle time at station number one. I would like everybody to try that for station number two. What would you have for station number two? What minus what equals what? Please feel free to share your answer. Something with my Zoom. So she got 4. Jaylene also got 4. Elita 4. How about other students? What do you think? Also got it 4. Dylan also got it 4. You know what? You are all correct, right? So let me write out the equation with you. We have, so we pay the workers at station 2 to work for 10 minutes. So that's why we have that 10 right here per car, right? We pay the 2 workers at station 2 to work on the car for 10 minutes, 5 minutes per each worker, right? But then by the nature of the RIN's activity, it requires only 6 minutes of work. So definitely we take 10 minutes paid time minus 6 minutes actual work time, right? Then we would have the idle time of 4 minutes at station 2 per car. In real life, what does that mean? So the car will show up for 5 minutes, right? And because there are 2 workers at station 2, each one of them only have to work, each one of the workers only have to work for 3 minutes. In total, it is 6 minutes required. But each one of them only have to work for 3 minutes. And then the remaining 2 minutes, they stay idle, right? The car only requires 3 minutes for each of the worker, and the remaining 2 minutes, the car is already done. The workers do not have to work on the car anymore, right? And because there are 2 workers, so 2 minutes per worker times 2, so we have the idle time of the total idle time of 4 minutes per car, right? What do they do when they have idle time? They can chat, they can make phone calls, they can do other things, right? So as a manager, maybe we're not happy with it. They play during the work time, but you know what? It is not their fault. It is actually our fault. We misconfigure the process. That's why they have the idle time. They, it's perfectly legal for them to not to work during the idle time, because why? Because the car is already done and they are waiting for the next car to come up. How can they work, right? They are still waiting for the next car to come up. So that's why they have the idle time. So we have 4 minutes idle time at station 2, and actually it is our fault. It's not the worker's fault. And at station 3, by now it should be easy for everybody, right? We pay the workers to work for 5 minutes, and by the nature of the dry activity, it takes only 4 minutes. So the worker will have 1 minute idle time. And again, it's perfectly legal in the quote, okay? Here, because we talk about the car wash, it's not about a law process, a law. So we have 1 minute idle time for each car at station 3, right? So in total, we can add them up. And then we have 0 plus 4 plus 1. Then we have the total idle time, TIDT, as 5 minutes per car, right? For each car or per car, we might overpay the workers for 5 minutes. It is our fault. We cannot take the money back. We hire the workers to work for the whole day, but because of the misconfiguration of our labor force, we overpay the workers for 5 minutes per car. Okay, so that's the idle time, right? I hope you see how we got the answer here. By the way, do you have any question for me about what we have so far from the beginning? Please feel free to ask me along the way, okay? You don't have to wait until the end or anything. Just please ask me as we go. All right, so after we calculate the idle time, now we can calculate the next one. So we call that as the, so this one is called the employee utilization. Right? So we hire the workers to work for us. We pay this much to hire them. Then how much of our expenditure is effective? So how to calculate it here? Let me work on the first one with you. And then I would like to ask you for the second and the third. So we pay each worker to work for 5 minutes. I'm sorry, I'm talking about the station number 1 only, okay? So we pay the worker over there to work for 5 minutes. And that worker actually works for 5 minutes per car. Everything here is per car. So we divide them up, right? Then we have 100% employee utilization or labor utilization at resource number 1. So it means that the equation here is we take the labor content, we divide that by the paid time, right? Then we will find our labor utilization. Okay, so how about the second station? I would like you to try it. Oh, C is very fast. And another student, please try that for the second. So Christopher Finnan and Michael have. Okay, Alida VE. Okay, so all of you got the same answer. That's very good. So the concept here is we pay the workers to work for 10 minutes, right? 5 per each worker, but then we have 2 workers. So at station 2, in total, we pay them to work for 10 minutes. But by the nature of the second activity or the rinse, right, it takes only 6 minutes. So we take 6 divided by 10, and we have 60% labor utilization at the second station. The third station should be easy for everybody. So let me work on that with you. So we pay the workers to work for 5 minutes, or the car shows up in front of the workers for 5 minutes, right? So we pay the workers during those minutes, 5 minutes. But then by the nature of the dry activity, it takes only 4 minutes. So we take that divided by that, then we have 80%, right? So we call these as an employee utilization. But at the end of the day, we want to calculate the average, right, among the utilization here. So we need, the next step is we need to calculate the average labor utilization. So this part of this row right here, it has an individual number, but the last number is called the average labor utilization. Okay, so employee utilization and average labor utilization, or ALU. Okay, so what is the average labor utilization right here? If you recall what you read in the book or on Connect, then you should see that there are 3 methods to calculate the average labor utilization, right? So let me show you how to use the 3 methods to calculate the average labor utilization. C, you got an idea. That's good. Along the way, we will discuss what C just mentioned. All right, so here we talk about a very important concept for the average labor utilization, or ALU, right? So there are 3 methods or 3 equations, and here's the first method. The first method, we call it as a definition method. By definition, the average labor utilization is an average over the workers' utilization. Right? That's why we call it the average labor utilization. Here we look at the workers. We know each worker utilization. So we calculate the average over them. Then we're gonna find the average labor utilization. Do you know what is that here? Let's try. So by definition, right, we know each of the workers' utilization already in the previous part of the table. We just calculated earlier, employee utilization. So what would be the average labor utilization among the workers? Or how would you do it? Right. I got the first answer from C. And of course, I would like everybody to think about how to calculate that average labor utilization, or the average workers utilization. How would you calculate it? Okay, so I got another idea from Philip. Right, so I encourage everybody to think about this. So Lynn got another idea at the averages from the labor content and divide by the number of station. Okay. So C said that, yeah, so now there are 4 workers in our process, right? Marco got another idea like C earlier. Take 15 divided by 20, right? But I would say that that's not the definition method that we are trying here. What we are trying here is we already know the workers' utilization. So we need the average over the workers' utilization, right? So actually, Philin gets a very great idea, a very clear idea. Let me go through that with you. By definition, right, the average is a sum of the utilization divided by the number. So the ALU in this case is going to be the utilization of the first worker plus the utilization of the second worker plus the utilization of the third worker. But the third worker and the second worker are working at the station number 2. So the 2 of them will share the same utilization, right? So for the third worker, we should have 60%. 2, right? The second and the third are working at station 2. So both of them are 60% utilization. And the fourth worker is at station 3, that worker's utilization is 80%. So the average is we sum them up divided by 4. We sum up 4 numbers divided by 4, right? So in this case, it's going to be, if you calculate it, it's going to be 75%. So that's the definition method, what it means by the average. So that's the first method. The second method goes as a following. Another equation that you see in the book, okay? So the average labor utilization equals the labor content divided by the labor content plus the total idle time, right? Okay. This equation can be easily understood as the following. We take the labor content divided by the total paid time. Because the total paid time is a total between how much work is required and how much work or how much time is idle, right? How much time that the workers actually work plus with the time that they do not work. So that's the total pay time. If we take the labor content divided by the total pay time, then we also can find the average labor utilization, right? So in terms of the number, we write here as we take the labor content is 15 minutes per car, and we divide that by, maybe I should write it on the other side. So equals 15 minutes per car. That's a labor content. How much work time is required per car? And divided by the total pay time, if you look at the table, right, we calculate the total earlier, then it is 20 minutes per car, right? So 15 divided by 20 or 3 divided by 4, then we also have 75%. So actually the second method is equivalent to the first method. It is a shortcut Why? We bypass the average. We just calculate the actual work time divided by the total peak time. Then we can also find how efficient it is, right? So, and then earlier C and Marco got the idea, and it is what we are doing here in the second method. And in the third method, we would do it as the following. And this equation, let me tell you, it looks very strange, okay? The average labor utilization equals the labor content divided by the number of employees. And the whole thing divided by the cycle time. What is that? Why do we have this equation? Okay, let me explain. So we know the following. We know that for each car, we would have 5 minutes to work on it, right? So the cycle time here is 5 minutes per car per worker, because the car will show up in front of you for 5 minutes. So you have that time to work on the car for 5 minutes, right? For each of the workers. The question is, how much of those 5 minutes do we actually work on the car, right? That's the numerator of this ratio. So that's not easy anymore. The labor content is how much time that is necessary for us to work on each car, and then we hire this many workers. So the labor content is kind of average, is divided among the workers, right? So that's why we had the top equation. So we take 15 minutes per car. That's the required work time per car. And then we even out over the 4 workers, right? So we have 5 minutes per car to work on, and then this is how much we actually work on a car, on average per worker. So if we look at this equation, the minutes per car will be canceled out, the workers will be canceled out. So what we have left is we take 15 divided by 5 times 4, right? And eventually that's 15 divided by 20, and we have 75% one more time, right? So that's our average labor utilization. No matter how we calculate it, the 3 methods will generate the same answer, right? Because actually they are telling us the same thing, even though the forms of the equation are different. But the notion here is we spend this much money or we pay this much time for the workers to work on the car, and how much time they actually work, right? That's our usage and efficiency right there, right? So let's go back to the table. Now we already have the answer, right? By the first method, we got 75%. The second method, you also have 75%. And the third method, we also have 75%, right? So when you work on the question 25, you can do the same like what I do here. I show the equation outside of the table, and then I put the numerical answers back into the table like this, right? Okay, so with that, we are done with the calculation of this question. The only thing left is, Gerardine, if you want to work this in Excel, is okay, but then beside the Excel work, please show me how you get the number. What subtract what equals what? What divide what equals what? I need to show the work. It's not for me, okay? For me to grade, but eventually it is for you to really understand what how you got the answers. So the final question is, as the manager, right now we see that we only have 75 efficiency here. It's bad, right? We spend, for example, $100, only $75 are effective. That's a bad thing. So what to do? in this case, right? So in this case, we misconfigure the labor utilization, the labor configuration. So that's why this utilization is very high, that's very low, that's medium high. So the process is not balanced in this case, right? So as a manager, we should balance out the process first by cross-training the workers, and then reassigning the workers in real time, so that if a station is kind of short on people, then we call another worker to come in and share the work, so that we can speed up the process at that bottleneck station, for example, right? So that at the end, all the columns of utilization will be equal, and then with that, now we can take more demand in, so all the utilization column will reach 100%, right? At that time, we do not have any idle time at all. And we are totally efficient with our labor force. Okay, so that's the idea behind this, behind all this calculation. So we are done with that efficiency measurement topic, and the very final topic of this module 4 is about process improvement, or how to improve the performance of the process, right? Okay, so the first method is we staff our process according to demand. So staffing according to demand. So if we have more demand, we staff more. Of course, you have to balance out the process first. And then we see that we still need more people. When we staff more, we hire more, we call more temporary workers to help out with the work, right? So the first method is staffing according to demand. In the textbook or in the slide, there's an equation. You don't have to worry about that equation for now. We're going to learn that later in the later chapters. Okay, just the intuition. Okay, when we have more demand, we need more workers. We have less demand, then we do not need that many workers, right? The second idea to improve our process is we need to offloading the bottleneck. So the bottleneck is the one that limits the flow and the stream of revenues. So somehow if we can relax the capacity, or we take away some work of the bottleneck, then more things can go through the whole process, and we have more revenues, right? It means that we are using our resources more efficiently. The third method is balancing out the process. And we talk about this many times, right? We need to cross-train the workers, and then we assign them. And the fourth method is labor specialization. All of these are conceptual discussion. If you read in the book, they will talk about sometimes it is good, sometimes it is bad, right? So I encourage you to review this part of the a little bit in the slide, and also in the book about how to improve the process. All of these are kind of a conceptual discussion. So I would like to end the class here. I wish everybody a great weekend, and I will see you back next Monday, right? I hope everybody is ready with the remaining question this Friday. So you should have enough time to finish everything, right?